Yeah, first of all, Edouard and Peter, thank you very much for this invitation to this great workshop discussing abrupt or not abrupt. And I would like to contribute to this. And we have heard so many things about data, so I try to avoid data and talk mainly about theory, concepts, modeling. Yes, some reality check, but very briefly, I promise you. And then going on with some alternative interpretation. So talking about theory, well, perhaps Alexander von Humboldt was the first who talked about abrupt change in North Africa. In his book, View on Nature, actually one of the few books that he actually wrote in German, he talks about deserts and steppes, and he considers, or he comes up with some ideas why there's such a big desert in Northern Africa. And he puts forward a number of points, and then he goes on and say, perhaps it's not sufficient, and perhaps there was a revolution in nature, abrupt climate change. For example, the flooding ocean that has washed away the fertile soils of Northern Africa. So he thinks that, actually he specifies it as a North Atlantic subtropical current that was supposed to be much faster and then spilled over and then washed away. And that happened, as he says, in the deep past, so in Paléoclimate, and, well, just a speculation. Okay, so that's the first theory. The more modern theory was put forward by Rudolf Spitaler. He, as several companions of his age, like Milankovitch, thought that orbital forcing triggers climate change. And not only the ice ages, but also, and that I think was his original idea, the changes in monsoon. Because he says the change in the orbit of the Earth's orbit around the Sun is affecting the insolation, such that we have a high insolation in the mid and early Holocene in summer, so that the temperature gradient between continents and ocean is stronger than today because of the large heat capacity of the ocean. So that is the idea that has been long around, and also in the 1980s and 90s, when we did paleoclimate modeling. I think John Kutzbach was the first. So the outcome of this is if we feed the orbital parameters, meaning the insolation changes, into an atmospheric general circulation model, we do get some enhancement of precipitation, but pretty much south. So the southern rim of the Sahel zone, but not very far in the north. And if we try to diagnose vegetation change from these precipitation changes, you find, wow, a big desert. So there's something missing, although the triggering is there, and the missing agent is vegetation itself. If you get some more precipitation and you allow for vegetation to change, to enter the desert, then it spreads. And that is seen in the old simulations by Pascal Baconneau and myself. And actually, we have a big greening here, and there's also some strong greening due to atmosphere and vegetation, and the ocean adds to this further on. Now, these are old simulations, but basically, the qualitative conclusion remains the same. Just recently appeared a paper in Climate of the Past discussion with the newest version of the CCM Earth system model that precisely produces the same. And why? Well, the Sahara is something special in the climate system. It's an anomaly. It's a cool spot, actually, if you wish. So normally, in the tropics, you get much more energy in than energy leaves the atmosphere due to long-wave radiation. And of course, in the high latitudes, here this is a summer figure, so that's in Antarctica and the exotropics, and much more energy leaves the atmosphere during outgoing long-wave radiation than it enters due to insolation. Now, the Sahara is an anomaly, specifically the Bodele depression. I mean, it's negative. So even summer, you get less insolation in than energy leaves the atmosphere into space. So therefore, it's a cool spot, and that sets in motion changes in the atmospheric motion and the atmospheric circulation. And I would like to remind you that this changes then in the atmospheric circulation. It's regional scale and large scale. I just want to point out and remind to you that the tropical circulation actually is not homogeneous over northern Africa. I mean, that was pointed out earlier. You see there's a strong difference in circulation pattern, atmospheric circulation and surface air pattern here. In the western part, you have a heat low here, and then in the eastern part. So no surprise that Western Sahara and Eastern Sahara should behave something differently. And I would like to point out, because it came up earlier, that also the ITCZ, the intertropical convergence zone, is something, well, that's much more complicated than, for example, over the ocean. So over West Africa, the rain belt here is south of the convergence zone. So ITCZ is, or maybe we shouldn't call this ITCZ anymore. That's perhaps the intertropical front here, where the Harmattan moves in and the monsoon comes in. So we have some rain here, but the main rain belt is here. And this dynamics is governed pretty much by what we call the African easterly jet. Okay, so this is the basic picture, the basic understanding. And now you talk about dynamics. Here we discovered many years ago, almost 20 years ago, some interesting features. Again, old figures, but still valid conclusions, because there are 3 more models that show pretty much the same figure. Most recently, the paper just mentioned that is in Climate of the Past discussion. So what you see is that the model, if you just run it for present-day climate, for mid-Holocene climate, would produce not only one solution, but 2 solutions, depending on how you start the model. I mean, there's nothing surprisingly for people thinking about nonlinear physics. So most nonlinear systems do have this property of coming up with multiple solutions. So, but the interesting thing is that for present day, we do find 2 solutions. Also the possibility of some green Sahara, also it's not occupied, of course. And then in the mid-Holocene, in this model, well, we don't find 2 solutions, but a solution that is pretty much the same. So, I mean, that might be just due to random differences. So, and that provoked us to say, well, maybe it's theoretically possible that there would be an abrupt change going from the green state to the desert state. And why is it so? Well, that's nonlinear physics, and I would like to explain it very briefly. It's a very simple concept in principle, but with a number of complex conclusions. So just assume that vegetation depends on precipitation in the semi-arid areas. And if you have just too little precipitation, then we have a desert. And if precipitation is large enough, we have a green landscape. And vegetation coverage changes something like this. I mean, this is the very first approximation that we say it's linear. It's just for easy calculation. And vice versa, if you look at the precipitation is stronger over a greener surface than over a desert surface. That's what we observe, actually, and can also understand quantitatively in semi-arid regions. Now, if we now let vegetation and precipitation interact with each other, so that precipitation depends on vegetation and vegetation adjusts to precipitation, then the solution of this dynamic interactive system is just are the intersections of these curves. So in this case, we would have 3 solutions, a green one, a desert one, and something in between. Well, this something in between is an unstable solution. So it's just an equilibrium solution, like you put a ball on a tip of a mountain. It won't sit there. If you have a slightest perturbation, a slight change of wind, it would tip the ball over the hill. And so it's never realized in the presence of weather fluctuations. So you would be either there and, okay. Do we have another pointer? Sorry, it's there or there. Okay, this is the case in the semi-arid climate. And if the battery is a bit low, no, yeah, maybe you should warm it up. So thank you, Jess. Great, yeah. So now let's assume that the climate changes, the background climate changes, so that this threshold value here changes from humid to dry. Then the blue curve changes to the left. And what we have in this case that we have one solution, two solutions, and one solution. So it's conceivable that while climate is, or the background climate is changing progressively, gradually, then there's a jump in this vegetation and precipitation coverage. We might call this, this is a sensitive plant type, a plant type that reacts to precipitation very sensitively, so it's a steep curve here. And sometimes you also refer this as a strong interaction, because this plant, this sensitive plant type, in interaction with precipitation, produces an abrupt change. Let's look at the resilient plant type, so plant type with a much shallower slope. In this case, if we proceed coming from humid to drier, we have only got one solution at a time, and it's conceivable there's no abrupt change anymore. So we might also call this a weak interaction. And if we put now this conceptual model, and I mean, there are a number of parameters hidden here, this one, and here also a number of parameters, fit these parameters to observations or model output of the comprehensive models, then we can do a simulation of the last, 6,000 years with this conceptual model. And just for the sake of reality, we add some precipitation noise to represent climate fluctuations, fluctuations in sea surface temperature, whatsoever. And what we do see is that the sensitive plant type in interaction with precipitation, has a pretty abrupt change here. Because the forcing is linear. It goes like from here, just straight down. And this is an abrupt change. And in contrast, the resilient plant type has, some fluctuations, but it has a gradual decline. And interestingly, the precipitation in the case when the resilient plant type interacts with climate also has a kink in precipitation. You don't see it when the resilient plant type interacts with climate. However, this statement is true only in the statistical sense. So when we're doing lots of simulations with this system, many of them, hundreds, you would see this in most of the cases. However, just by chance, what you can get is something like this. You have here a resilient plant type, the same as before, but just another realization, just by chance. You see some abrupt changes here at that time, even with the resilient plant. And I think that's very important, because it means that if you have got only one proxy and one proxy record, only one, then you cannot make a definite conclusion saying, well, I don't see an abrupt change, therefore we have a weak interaction or something like this. Or we do have such a kink here, and therefore it has to be a strong interaction. Well, it could be just by chance that this resilient plant type, apparently weak or seemingly weak interaction, produces something like an abrupt change. And it also appears here in the precipitation. And that was something Zheng Liu, my American colleague who also thinks about abrupt change, mentions. He thinks that having a gradual decline in precipitation or an abrupt change in precipitation makes a difference between strong and weak interaction, and I say no. In statistically, yes, but it can happen that you find also abrupt change in the weak interaction. Okay, so that's just by the remark regarding the stochasticity of the system. Now, this is a conceptual consideration, very simple modeling, and what do the more comprehensive models show? And this was already mentioned by Peter. This one was the first prediction, if you wish, a prediction of the past, showing that we do have here at 5,500 a regime shift. That's really a kink here, and it can be shown that it is a tipping, so to say, from one state, from the green state to a desert state, but then it levels off more gradually. So there's definitely a regime shift in this model here. Well, we do have another model which shows some gradual fluctuation, but more noise in this area, and the authors think that here we would have something like flickering, which means the system has two states, but because of the weather noise, it cannot decide in which state it should reside. So it goes back and forth, and then if there's only one state left, the desert state, that settles in there and continues with fewer fluctuations. Now, we have criticized this point lately, but anyhow, just for conceptual thinking, it could happen. And the last one is the what we call the stable collapse. In Singulius run, we have a gradual change in precipitation, but just this kink in vegetation, which could be indicative of having a stable collapse. So just vegetation following precipitation. And for some reason, well, the vegetation is pushed more to the green, and then all of a sudden it goes more to the desert state, although that's only one state at a time. And then, of course, we also have the example of the, what I would call, boringly linear case. I mean, that's something I don't want to see, but it's our model, actually. Goes all the way down. So we start here, and then, yeah. So, okay. So far about theory, modeling, concepts, and so on. Now, with reality, I can be very short. I'm very brief, because you all know this. It was shown today. We have this dust flux, so now that's definitely not gradual. Yeah, I asked Jessica whether this point is real, and she insists it is real. So then it's definitely really abrupt. And Stefan, well, we see a lot of wiggles here, and you say it's gradual. Well, okay, let's put it on one scale. And so all the three models, actually it's from an older paper, so we have more records now. And I put here also the 14 dates by Pahur, also a very old paper, but you see here some fluctuations, and then boom, the system settles, looks like this, but I don't want to overinterpret this. Now, you could, of course, just play with these curves and just put Peter's curve on Stefan's, and yeah, I mean, these are just the tropical taxa, no? And then they have pretty much the same slope here, and Jessica's curve, and well, a bit shifted, but yeah, this is really abrupt. If you just omit this, it's not, but if you, it's really abrupt. So the point is I would like to make is, and then it has been said earlier, it would be worth an exercise to say, let's get all the paleo data and all the model simulations on one scale, so to say, and then define abruptness in terms of rate of change. We could also, and we did it now recently for many model simulations that go into the future, so the next 100 and 200 years. So we took, say, 12 models and looked in all model output, and then just screened it and say, where do we see any abrupt change? And so we see something in sea ice. So we identified 44 abrupt spots. And then, okay, that's not yet published, but we could do the same. Let's get all the records in the proxy and the simulation and just see where do we see something abrupt. And we define abrupt, maybe a single change, or this is also an abrupt change. I mean, you have some mode here, it goes up and down, and then the system is silent in a way. No? So Stefan, we definitely look forward here on seeing more on this here, and if the topical taxa go like this, and I would say there's a regime shift going from flickering to botanical. Okay, now, as promised, alternative interpretations. Again, just fantasy, some idea, theory, and concepts. If we go on with more complex models, then we see that the idea of having multiple equilibria can be pretty complex, yeah. Because in a model that's more geographically explicit, like this one here, you see all the grid cells, you see the situation that the differences or the number of equilibria and the pattern and the difference between equilibria can change. For example, this model develops 2 equilibria, and the difference between the equilibrium states is marked here. So one state is much greener here, and the other is less green. And later on, 3,500 years later, in this model, all of a sudden this vanishes here, but then we see multiple states here, or with 2 states which differ in this region. And accordingly, at that spot here, not spot, it's a grid size, it's 300 by 300 kilometers. So this little region here, we have an abrupt change around 6,000 years, and here a little bit later. So that means, I don't want to say that's now the completely realistic simulation. No, it's just a conceptual consideration. So I would conclude from this that it is theoretically possible that the idea with the multiple states is much more complex, that states change, and that we can have abrupt vegetation change at different times at different regions, and also no abrupt change in some regions. Now, I must admit, Lake Eowa is just here, so in this model it should have had an abrupt change, but maybe it hasn't. But maybe this might be not a proper recapture of multiple states. Okay, so that's one point, and I would like to go on and say, well, even if we look in this, into this seemingly boringly linear case, vegetation coverage is just one side of the coin. There are other sides. This is, again, vegetation coverage of this model at this point here, at 6K. You see a lot of greening here. And Florence, I should say, these crosses here are very important. These crosses indicate that on average it looks like a desert, but once in a while, in a few years, for a few years, you do have some greening. And this indicates that in all over the Sahara, there, by chance, you have periods in time where you do have some greening. So this might be also interesting for interpretation of pollen records. There might be not necessarily, we don't have to have necessarily a complete and long, consistent coverage by vegetation, but it could just be happen that we have some vegetation there, and then there's a silence for another 100 years, and then we have just another decade of blooming, and then it goes away. So it could be enrich our interpretation of pollen. Now, the point I would like to make here is that if we start from this here and that go down, then we see actually linear or with fluctuation change in coverage. It's a thick line, but the carbon stored in the living biomass, it's this thin line here. Well, this goes up and then it goes down here. So that's really much more abrupt. So it might be just the way we look at vegetation coverage or the structure of vegetation. So we can also have abrupt changes in structure. Now that leads me to a second proposal. If we look at Stefan's data, I mean, they're really rich. And you see that the tropical taxa, and then here the Poaceae, there's the influx, and the acacia are still there, and here are new plants coming in. So the biodiversity changes a lot. So, I mean, so then the question could emerge, does this matter? I mean, is it so that we have perhaps some resilient plants, some unstable, some sensitive plants, and if we mix them, does it have any effect on the stability of the vegetation-climate interaction? And just to explore this idea a little bit more in mathematical terms, and we can use our simple model that I showed you earlier, just by saying, now the precipitation doesn't see one type, but it sees the average of both vegetation types. And each vegetation type, the sensitive and the resilient plant type, sees the same precipitation. So that is some plant diversity just in terms of moisture requirements. So nothing about dominance or competition, just moisture requirements. So very simple. And now if you put this into our model, now this is the, again, the case where the two plants, resilient and sensitive, interact individually, and now they should interact jointly. And what we do see is, well, the resilient plant get much stronger fluctuations. Well, it dies off a little bit here, but the lifespan of the biosphere is the same. It's still there when the tropical taxa. No, sorry, I don't want to say this, but the resilient type is gone. But the lifespan of the sensitive type, the red one here, extends. And of course, the synchronous fluctuations, well, that's the way we constructed the model. And even more importantly, we do see a fairly gradual change in precipitation. So that means, or from that we can conclude that yes, plant diversity affects the climate interaction such that it in a way stabilizes everything. Even if you have some resilient plant types that would produce abrupt climate change, if you put them together with others, it just smoothes out. And we do have strong fluctuation in the occurrence of the taxa, but the precipitation is fairly gradual. We can go on and even show that even if you have a number of sensitive plant types, you don't need resilient plant types, sensitive plant types. Each of them just give rise to flip-flop. And you put them together. They just have to have different thresholds. Then the biodiversity, then the plant diversity stabilizes everything. So from this, one might conclude that you would see abrupt vegetation and climate change only in areas which are poor of plant diversity. And in regions which are rich of plant diversity, this system looks much more stable. And of course, the question of strong and weak interaction becomes in a way obsolete, because you can have strong interaction individually and then put plants together, then it looks like weak, also you do have a strong interaction. Okay, so that's concepts about plants. And the third point I would like to make is, well, it also came up, but I basically repeat it here. This is a dust flux into the Atlantic, and we saw today many more of them. And here are hydroclimate proxies. And even in the Lake Eure, you see an abrupt change in the aquatic ecosystem. It goes from a sort of a freshwater system abruptly into a saline regime. So you do have abrupt change, a very abrupt change in Lake Eure, but only in the hydroclimate in a way. So we could assume that maybe this is plants change, but that doesn't matter for the dust flux and the hydroclimate because there are nonlinear thresholds in the interaction of the hydrosphere with the atmosphere. For example, and I borrowed this conceptual view from Sharon Nicholson, just imagine a lake, and if you have a gradual decline in precipitation, then the lake becomes shallower, and then it dries out, and then all of a sudden, from here to there, the area covered by a wet surface goes away. So the potential dust generation goes up non-linearly. It has nothing to do with plants, just soil moisture and a constant decline in rainfall. Or in the aquifer, the change of rain might take somewhere else, so it just feeds the lake. And actually, we do have some evidence, even in our boringly linear model, that the area of saturated or near saturated soil declines not linearly, but faster in this region and less fast in that region. So I will have hopefully soon a doctoral student who then really explores hydrology in our model and dust generation of our model and the occurrence of lake level. So is it possible to have onset of abrupt changes in this regime? Okay, the fourth point that was put forward by Sharon Nicholson in many of her papers, she observes, together with others, that Sahelian rainfall has a bimodal distribution. And so does have the African easterly jet, a bimodal distribution in its location. So when we have a more wet, strong Sahelian rain, wet region, wet mode, then the African easterly jet moves north. And if we have a dry mode, then the African easterly jet is more on the southern part. Now, I mean, this is 14 latitude and it's 16 to 17. And also the wind speed near the surface, the so-called African westerly jet, changes. And also the tropical easterly jet, that's fairly high, near 200 hectopascal, more to the equator. So actually it's between the tropical easterly jet and the African easterly jet at the outer edge of the rain belt, so to speak. It also has a bimodal distribution. Now that, and Sharon says, well, there's nothing with vegetation, nothing with soil whatsoever. It's just an abrupt change in the mode of operation of the African Easterly jet. I'm not quite sure about that, because that would really mean that you have an abrupt change in precipitation. And as far as I understand, that the change in precipitation is indeed more gradual. Okay, but I would like to just mention this. Now, a fifth point, which it's not really a question. It's more a statement of a challenge. And so the point is really, do we really understand climate or climatic change in the tropics? I mean, know about global climate change, that's fairly basic, but now the specific response of the tropical circulation to climate change. And if you look in 4 different models, and that was done by Björn Stevens and Sandrine Bonny, shows the following. Very simple experiment, so no vegetation at all, to make it very simple. Just an aqua planet. So a planet like ours without any continents, just an ocean. No? And then all of a sudden you heat the ocean by 4 degrees, make it a little bit warmer. And then the model responds to it. And what they show is they respond pretty much the same way, the colors are a bit weak, in the exotropics. So it's a little bit of a drying here and a wettening here. And that's a scene basically in all models. And that's fine, because we really do understand how the exotropic work. I mean, because basically weather smoothes out the gradient in moisture and heat. So that's what all models do, more or less. But in the tropics itself, the inner tropics, the models have quite a different response. So, and then obviously, these 4 climate models respond to a very simple climate change in a completely different way. So therefore, we are really hesitant to say, well, do we really understand climatic change in the tropics? The specifically is also okay. So we will work on this. We have actually set up a big project on tropical vital boundaries at our institute to really pinpoint now why are these models different? What are the processes? I guess it has to do with the completely different energy cycle in the atmosphere in the tropics versus exotropics. The exotropics, you have the strong gradient between North Pole and the warmer low latitudes, and then you have the weather, and then the energy goes from the large scale differences into the weather pattern, and then the small scale, and then it goes down to turbulence. Now in the tropics, it's completely different. In the tropics, you have a spot convection, and that pushes energy into the circulation, and then you have changes in the large-scale circulation. So it's the energy cycle in the tropics is different in the high latitude, and therefore you need to resolve these convective activities in the tropics. You need really high-resolution climate models to do this. Actually, that's a proposition we have put forward and that we would like to test. Okay. Now I come to my conclusions and questions and challenges. I would propose that indeed we have a basic understanding on how the African humid period works. I mean, basic, I would say, so that's a triggering by orbital changes and some amplification by the ocean, by the vegetation, on the time scale of glacial to interglacial. And to isolate this, you really have to do careful numerical experiments. I mean, there was this paper by Pascal Balconneau, the famous PIME paper, where she admits that, well, talking about feedbacks was not possible because the models used were run in a different mode and for present-day climate and another mode and for Holocene. So you cannot really, you try to compare apples with pears. So that wouldn't work there. But really having the same model, the same setup, this, using just for mid-Holocene configuration and present-day configuration, and then switching off and switching on the proper, switching on and switching off the climate system component properly, then you can really isolate the vegetation feedback and the ocean feedback. And again, with the latest paper that appeared in Climate Path Discussion, did this and confirmed what we know from the earlier runs, that yes, the vegetation atmosphere interaction is positive in a sense, amplifying on a time scale of glacial, interglacial, glacial, and so on. Okay, so then things get interesting. Theory suggests the possibility of abrupt termination of the African humid period, but only some models and some proxies reveal some abrupt changes. So the point is really what is abrupt? I mentioned this, and indeed it would be nice if we just sit together and just put the data together and look, screen them. No? I mean, it's a proposal. And then, of course, it's conceivable that, no, it's for certain, I would say, but it's unconceivable that the Sahara is a big entity that just behaves homogeneously and does tips once for all. No, actually, it's a comprehensive, it's a very complicated and complex system, as shown many times before. Large, 9 million square kilometer, big area. The western part differs from the eastern part. So it's really conceivable that we do have abrupt changes in different regions at different times, and no abrupt changes in some regions at no times, at all times. So sorry. So, and here, yeah, I mean, it would be interesting to have a consistent and complete, in quotation mark, screening of proxy data. So it would be great to have many more Lake Yoas. But Stefan told me that there's only one Lake Yoa, and the other lakes are not usable for this. So we might have only one great vegetation pollen record through the Holocene. And to judge the difference in precipitation change, vegetation change, you need these independent information. And then, okay. So, yeah. And then the question of abruptness, yes or no, and do we have to expect abrupt vegetation changes? I think most models, and that's also when I started the very simple conceptual model, assume that's vegetation. Now, vegetation is also not homogeneous. No? I mean, we have different plant types and so on. We also expect then, therefore, biodiversity on plant diversity. So different plants react differently. And there's a nice work by our French colleague Anne-Marie Lezine and Christelle Elie talking about biodiversity, and then they show that biodiversity has changed a lot. Now I have a doctoral student who has a bachelor in biology and a master in climate system modeling, so she wants to reassess our model, whether it really captures biodiversity and what Christelle and Anne-Marie observe, and then try to see whether our model does it, and then put it in our model and try to get a handle on whether our models really describe properly plant diversity. Okay, so that's this point, and then of course, yeah, we also have to look into other thresholds. As I said, it's very likely, it's conceivable that we do have thresholds in hydrology, and we will yeah, look in our model, into our models. I mean, most climate system models, well, if they treat dust at all, they just put it into the atmosphere because it's important, yeah? But the dust generation, the uptake of mobilization of dust, and then the transport of dust into the Atlantic Ocean, that has not yet been simulated and is to be simulated. And of course, last but not least, we have to improve our atmosphere general circulation models and to see now what is really the response of the climate dynamics in the tropics to different forcing. Okay, so this catalog of conclusion, questions, and challenges concludes my talk. If you thank much for your attention, and if you've got some questions, I think I still have a few minutes left.